This is a lecture about perceptual grounding of concepts, of relational concepts in particular. And I'll give first a little bit of introduction into what that means, and then I'll show you how we do this in DFT. And in terms of the previous lectures, this will be essentially something that is very much based on the concepts that we developed in the last lecture where we talked about binding. So remember, binding through space, having neurally or anatomically bound dimensions like color and space bound together, and then we were able to extract information that's in there or also assemble that. And we also showed it's useful for coordinate transforms. In particular, attention selection was important. Now, if you have a representation, for instance, of space here and color, then you can give a color cue, and that color cue would put in a two-dimension would be a slice of activation, and any input from the scene that's localized input, these little blobs are input that would specify both the location, like the screen object here location, and the feature value. And by putting in that slice, you can sort of bias the formation of a peak toward a particular object, and thus extract the location at which this object happens. So this attentional mechanism is very central to what we'll be looking at. So I just did put that in here to remind you of that. And you will now see how we can achieve cognitive stuff with that. And similarly for the coordinate transforms, I don't want to go through that again, but you'll see that plays a role. So when you have a representation in one coordinate frame and you have a transformation variable, in this case it was the gaze direction, then you can compute where the spatial representation, where it ends up in that other reference frame through a bound representation of both the steering parameter, the gaze direction, and the retinal field. We'll do a little bit more abstract version of this in what comes. So the example that I will be looking at today, which is in part of our research activity here, a major part of our research activity is about what we call the perceptual grounding of concepts about relational language. And I'll explain that first, what that really means. And that's sort of our entry into what we call higher cognition. Ultimately, by higher cognition, we mean cognition that is increasingly far from the sensory motor surface, and ultimately maybe no longer really requires any direct perceptual input, so sensory input that you can do purely mentally in your mind. And I'll end on something like that, which we call mental mapping. So let's first clarify some terms and I'll give you a little bit background here. Of course, this is part of cognitive linguistics, and again, other lectures spent a whole semester on this, so I'll be very brief. So when you use language with talking to people, the most elementary form of that is to talk about the environment that you experience. Maybe let's say if you think in evolution, you talk to the other hunter, and describe, the tree you see right next to the tree, there's the lion, that's the one we want to shoot or something, right? So it's related to sharing an environment, talking about objects in that environment, and perhaps about actions in that environment, like giving instructions to someone to act in that environment. So here in this little toy example, you might want to talk about this cup here, say it's brown, and you, the speaker, sees that cup, and what you want to do is get the listener to attend to that cup. So we talk about the goal of that as, as the phrase, let's say the cup is brown, is then perceptually grounded if the listener is able to attentionally select the cup, to attend to the cup. That often means the person is actually also looking at that cup, because you said that, because you told that person to look at that cup or describe that cup or something. And of course, typically that will also mean that the speaker has attended to the cup. And in very many cases, it will, communication situation like that will entail what is called joint attention, in which both the speaker and the listener are attending to the same object, or it can also be an event. And actually language learning and a lot of communication is really based on that. In some way, this generalizes to higher forms of communication that I'm not elaborating here. For instance, if you talk to someone about, I don't know, the economy, then you are also attending to the same thing, saying, oh, the economy is hitting a roadblock. I always like that example because it actually uses this spatial movement, moving in space, hitting a roadblock. Our economy hits a roadblock and is stuck or something. That will be maybe an abstract topic you could discuss with someone if you're into economics. And you would also jointly attend to a concept, but the concept isn't something that is out there. Sorry, some object. It's not a concrete physical object out there. It's actually something that you only have in your mind. So I ended on this note that before we interrupt that, it said something about shared attention that could also happen in more abstract contexts where you're both thinking about the economy and therefore you're referring to the same object, mental object. Actually, it's like shared mental space. Kind of interesting idea, and actually, you will later see that we're completely actually thinking about how to create such shared spaces of attention. I should say that we, the dynamic field theory folks, call this perceptual grounding. That term is, there is no real consensus what the right term is. And there are different histories and so on. So I just mentioned that for you to, if you read stuff, you might be confused. So some people use the word grounding in another sense, for instance, in how these terms come about originally in learning. And there's someone called Talmi who has been quite influential in this, calls this targeting. But in targeting is actually, it's this question if it's really specifically about linking to perception versus linking just to, for instance, the mental images I was talking about. And some people also talk about referring, which linguists often talk about referring, that a term refers to something. But then it's often ambiguous if it's really referring to the physical instantiation of the object, like you're saying the cup, and it's really this specific cup out in the world, or are you referring to cups, the concept cup in general? And is, does that referral already, it's about the instance, about the category, there's a whole thing like that. So I'm trying to be very good down to earth right now. And all of his questions can be discussed, but here I try to be very concrete. And perceptual grounding really for us means that you're paying attention, ultimately acting on an object that you perceive and that the speaker is referring to. The speaker also potentially sees or saw or knows about. In fact, we're talking about here, we're talking about descriptive language, which is of that nature that you're seeing something and you're using relations to talk about that. And we'll see it in a moment exactly how. While there's the other part of it is imperative or imperative language, where you're giving someone orders, give me the cup, right? And that mixes both, because it means that you need to know which cup that other person is talking about. And also part of your realizing that action will be actually, that language will be to actually do that, to actually perform that action. And we do research on that. It's really exciting to us. But I'm not talking about it here. But you can see that it's always, such imperative language always involves also descriptive language, because you need to know when the action is directed at objects, and so you need to know which object to direct the action at. Okay, and the particular position that we take here is inspired by this embodiment theme that goes through the entire course. In the initial introduction, I emphasized that a lot. So we're always thinking about how cognition, this would be using languages, of course, a form of high-level cognition, but it is typically very closely coupled to movement and perception, and to and therefore to how your body is also in that shared environment. So, for instance, when you talk to people about objects in the environment, you use bodily forms of communication, like pointing, right? This most trivial part, like this little figure is pointing here at something. It's something abstractly called deictic codes, which is just Greek for pointing. And that might also take more general forms. For instance, you might be talking about something and you have already had a history with that person, and therefore you're referring back to something you previously saw, and therefore you don't actually need to explain to someone details about the object, because this is something that was already familiar from previous actions, and you could just implicitly, or even just a very slight gesture could, like toward a certain direction in the room where there is something that you previously talked about, could already help you to understand. And a lot more things like that are happening. And so that's, you can maybe intuit that a lot of people study language totally in isolation from these sort of things. And even though I will not be talking exactly about how to actually integrate these processes, you will see that the way we're doing this is very open to that. That is, it would be very easy to include in the process of attentional selection that we'll be talking about some source that comes from point inference, where you would be able to have a we actually did models like that where we took computer vision ideas to really observe an arm and extract the pointing direction from that, and then gave input to a field, a spatial field, that then in the end will do the spatial attention. That's where we're coming from. Good. So some terms here. So I will be talking now about spatial language. I'll explain that a little bit more in a moment. And when we do that, we're talking about targets and reference objects. So spatial language is one way of how you could guide attention to an object. You would typically, like here, you could say, the cup is to the right of the green book, or you would actually say the cup to the right of the green book. Typically, you would do that if you need to, if perhaps it could be reasons that the description is otherwise ambiguous, like you have a lot of cups and there's only, but you mean the one that's to the right of the green book, let's say. Or very commonly, this could be because the object is not so easy to find, and you're taking as a reference object something that's very salient. In fact, there's a part of the literature on visual search where people are automatically doing that. That is, if you're looking for a, I don't know, a casserole, you will, in the kitchen, you would automatically look near the stove, and you have a very quick way of figuring out where the stove is, because it's a very salient and large object. So famous example is if you're looking for the mirror in a bathroom, you automatically look above the sink. That's called an anchor object. So there are a couple of reasons why you would do that. Now that's specific. That's a specific issue about spatial language. And we, meaning the dynamic field theory kind of folks, started with spatial language. We were collaborating at the time with a cognitive linguist, and John Lipinski, whose work I'll be referring to, and he argued that that's a good entry point because this is a deep thing, and I'll say a little bit about that in a moment. So before I go there, another two words I have to characterize. So there are two directions of this, and just to clarify that, so one would be if you hear a sentence, what is to the right of the green object, for instance, that might be here, this, I don't know actually what that is, some reddish fruit, that you then direct attention to the object, and that's what I'm talking about, perceptual grounding. The other thing would be if you see an event or you see a scene, that how do you describe it? How do you produce a conceptual representation? We call this a conceptual representation. We use this phrase here. How do you generate a phrase like that? For instance, this comes from an older project where we took video input like that, and you see the operator here does something very simple, just moves around, moves the hand over this object and then moves the object around and so on, because our neural dynamics was just picking up very simple things, colored blobs on white in the hand, and so we were observing this, and then the system would generate something like the hand moved the red object, to the left or stuff like that. So these are the two directions, and we'll be looking in a moment at how to do both with the same kind of neurodynamics. The one is generating language, the other is interpreting language in a way. Now, all of this work, we're referring to language, but what we're actually doing is we're grounding structured concepts. So phrases are structured concepts. Say the green banana to the left of the right, the red tomato. I'm using concepts like banana and tomato and red and green and to the left of and so on. And so they have words, so it's part of language, but there are concepts, they're actually concepts that don't have words, right? When you describe something that is well known to you, then maybe you don't have a name for it, but you know it's a concept. And that's the level at which we're looking. And then there is, of course, many dimensions of language. Another dimension is really how to fill concepts like that with words, which means ultimately associating them with sound patterns, which is the most natural thing. And then even with written things, with graphemes and stuff like that, which is a cultural achievement. And of course, there's a lot of complexity in that, and we're not dealing with that. And in some of our work, it's actually important, or we have to assume that there is a language machine, a language processing machinery that extracts from heard speech or read written language, extracts the conceptual structure, that is, extracts what's the relational word, what is the target, what's the reference, and so on. And there's a lot of work, of course, on that. And actually, some of my colleagues in John Spetzer and Larissa Samuelson in East Anglia work exactly on issues like that with our dynamic field concepts. But I'm not teaching about that. You can imagine it's a huge area. Yes.
You test that the machine is actually extracting the conceptual structure and not only the statistical, for example, co-occurrence structure.
It's a huge question. So, I mean, this is a real topic of debate in this field. So there have been a lot of arguments why people actually extract structure. And there's structure, syntactic structure, and then there's actually structure at the semantic level. And we're talking about the semantic level here, but syntactic structure is used for that. And so there's a lot of classical arguments why, or that people do that, and they often rely on being able to interpret correctly phrases, correctly meaning understanding the structural dependencies for phrases that they never heard before, that are nonsensical and so on. And there was always the argument that that is not something that you could do just by using statistics. Now, in recent years, as you're, I'm sure, aware, purely statistical methods have performed in a way that seems to call into question these kinds of arguments in the sense that machine learning techniques, for instance, have been able to associate meaningful responses with phrases never heard before, and thus was able to extract somehow statistically from its learning material enough information to do that. And debate has just shifted debate because now it's a question, does that actually mean that that algorithm understands the phrase, or is it really just that it recognizes a pattern and completes the pattern, and the kind of things we say are highly reproducible, and so you can actually pretty much predict what's going to be said, and that will be the Searle Chinese room issue, which I'm sure you're aware of. I think technically speaking, all these systems are Chinese room kind of examples. That is, the algorithm really doesn't know what one is talking about. And that is a frontier of research. So there are people who are training these networks to do what we're doing here. That is, for them to be able to take a little videos clip and then generate a language from that, and to take a language and in the video clip select, for instance, the object that you're talking about. DeepMind, for instance, does things like that. So that gets very close to what we're talking about. And it's a real concern for us to understand what that means. It is tricky territory because, in a way, this is still only pretending to do that, because what these systems actually do is that they are making now the association between some stimulus material, the images, and the language based on having observed, in the training material, they saw that certain phrases are used with certain images. And in fact, the training material in these cases consists of labeled images where you have regions of interest, and people actually, the algorithm learns that when this phrase comes, this region of interest is relevant and so on. And so they're learning all of these things statistically. And And then there's always the question beyond that association that these items are learned, can they do something beyond it? And the problem is always, I made the move from language to grounding now, and then the next would be maybe, well, can they act on it? Can they reason on it? Problem is, any of those things you can actually ultimately learn. That is, you can imitate everything. You could, and so the debate is that how the brain works? Does the brain all the way down really just do everything it does by learning statistically the association, and then all the way? It's sometimes called end-to-end learning. You could have a system that learns to act. People are trying to train robots that way, that they know when I have that image, then I should press the gas pedal and accelerate, or turn the steering wheel. And they don't know anything about streets. They don't know anything about the rules of traffic. They just learned that statistically. So there are some people who really think that. And I'm convinced that it is truly wrong. That the brain is actually not like that at all. The brain actually also doesn't really need that extensive learning experience. So the old Chomskyan argument that there isn't enough material for learning, that was a very superficial argument at the time. A typical armchair argument that can be clearly dismissed. But I believe that ultimately there is some truth to the argument that we can now make much more precise. But I would say this is a very interesting ongoing debate, and currently a lot of people are sort of implicitly buying into this idea that you could, that there's no barrier to learning everything just statistically. I'm one of those who really don't believe that. And that's based on, for instance, the fact that infants will, from a single instance, start to make certain usages of things, and that that certain things are easy and other things are hard for humans. And so for instance, I will be talking now about spatial language, and spatial language is among the harder concepts of language. It's harder to learn new spatial terms and to use spatial terms in different ways. And that reflects properties of our brain, ultimately. Make an argument about that. Again, it's actually always, if you have a well-defined problem, then you can find an algorithm that also learns that. But it's not clear that is how it's done in the nervous system. So a question that hits right into a core issue of current research. Good. So yeah, let's talk a little bit about spatial language then, spatial relations. So, like the left of, on top of, in front of, toward the south, and so on. These would be terms of spatial relations. So they are, in some sense, deep. That is, they evolve slowly across different languages. There are a limited number of terms, probably about 70 to 80 terms, depending on the language. They are really, they can profoundly differ across different languages and cultures, and there's some subtle differences between them. So that's why we thought that was a very good entry point. I should tell you that, and some of you might know that from, especially cognitive science students, that there is a field of embodied communication. Actually, a branch of it came from cognitive linguistics, and there were people who were, like Lakoff is a name, for instance, in that direction, who argued that you could understand the evolution of language and cognition in general from some kind of sensory motor primitives. And one of those primitives were spatial relations. That you think spatial relations are if you master spatial relations in this concrete way, that you could lift them to higher cognition. So for instance, if you say, the economy is on its way down, you're using spatial relation down to talk about something abstract. And then one would argue that you could reach a lot of content using spatial terms. And there's a whole book about how to analyze language or speech into these kind of primitives from which it's built up by analogy. The second concept of that nature is the path concept. That is what I already hinted at, moving, that you say this moves to that, or on a collision course, or the economy grows, right? There's a movement concept that is used to talk about abstract things. And the third concept of that nature is the container object concept. Something is in something, or is outside of something, and so on, which you see, you can quickly see how that is very foundational in that you could say, a chicken is an animal, or, the animals, plants, and animals are, are biological systems. So conceptual hierarchies could easily be thought of as deriving from metaphorically lifting a container concept high up. So the choice that we're doing here isn't in that sense arbitrary. We're really trying to think, could we look at some of these primitives and then look at how they scale? And actually, there's concrete research in my group trying to look at that scaling. We're looking at analogy formation, for instance. But this is the lowest level that we're starting. Now, give you a little bit of sense why that is so odd. And again, I assume some of you might know this. So there's, for instance, quite striking evidence that some cultures use absolute spatial terms. So they would say a north and south, for instance, even on a local scale. Like they would say, for instance, your northern shoe is untied. Right, that would be the most extreme. There's a famous example where islanders would refer in absolute terms always toward the beach, or inland, or toward the beach. Or there's people in the Andes who refer to the slope. They always say uphill, downhill. Actually, I myself use a term in German, Bergski and Talski, which is a term you use in skiing in German that refers to the ski. There's uphill versus downhill, which makes a lot of sense in skiing. And my kids who are bilingual and who's German being their second language struggled with that, and it took me a while to understand that they struggled with that because it was using an absolute reference frame. It was outside their cognitive habit to think like that, apart from the struggle of actually skiing. So that already hints, that these are differences. So, for instance, this has been used as a model system to understand how, to this question of, does language affect how you think? An endless debate. And ultimately, the result of a lot of work is, no, it doesn't actually, really. It's not true that people who don't have a word for light blue really see light blue differently. That's not really true. But it does affect your cognitive habits. That is, if you speak a language like that uses absolute orientation, then you have a habit of knowing your absolute orientation. So people who speak these languages tend to be aware of where north is and keep track of where north is, even if they're inside a building. And they are very good at that, but there's no reason to assume that their brain is somewhat different. So it's just that they are very trained in that because they need it all the time. Good. And so to understand spatial language, you need to know about reference frames, and you will see in a moment that plays a real operational role. So if you're the speaker, you have a frame that's centered in you. You can say on my left, right? And that's from your point of view. So there's two aspects of this orientation, of spatial orientation. It's where is the center of your frame and how it's oriented. Right? So the center of your frame would then be in the speaker. And then you could still speak about absolute directions in the sense that, centered in me, but north, that means north of me, right? So it's relative with respect to the center, but it's absolute in direction because it really pointing to north. Or it could be, to my left, that is, it's centered in me, and then it is in orientation, it is relative to my orientation, right? To how I'm oriented. And then there's the problem of the listener. In this latter case, the listener has a problem, right? Because the listener needs to transform it back. And then there is even the possibility to have a third object to define the orientational frame. So we hear that all the time here in the area when they say I think they say the door in Fahrtrichtung rechts, in the direction of travel. I don't know. They even say in English, I don't know exactly which phrase they use, but it essentially says that right is now directionally defined in the relative to the direction which the train moves, right, along the train. So it doesn't matter on how you, the listener, or this abstract speaker is oriented. And you have that, you can have that, actually we have that in German and in English, relative to objects that have some inner orientation, and we actually did a model of that. So for instance, a car has some kind of orientation, even if it's not moving, it's parking, it has a nose, right? It's like a forward. And so you would sometimes use that orientation of the car to address, to define the orientational axis. This is actually a well-known subtle thing in some Latin languages. I happen to speak Portuguese, and in Portuguese there is a subtle difference, which also exists in some other Latin languages, that you would sometimes also use an object as the origin of this reference frame. So for instance, if you drive in a taxi along the road and you say, drop me in front of that car, that's a question. What does that mean? Does that mean in front of the car from the point of view of that car, or from my current point of view in front of, so that the car is further back? And in fact, in Portuguese, it is the latter. Well, in German, I believe it is the form, right? You would say vor diesem Auto, and hinter diesem Auto would mean, behind that car. And in English, I think English is like German. I knew that, I just forgot now, but I think it's like German. So this is sort of actually, I still struggle with that every time I instruct a Portuguese person about things like that. I always have to think which way it is. So it's not easy to change. So I could speak about this endlessly, and yeah, I actually have that example. So it's not, I can check if I was right. Good. So it's clear that these spatial terms are relational. So mathematically speaking, they are relations because they involve two arguments, right? Relations are functions of two arguments. That's all it is. And so one of these arguments is what we call the reference, and the other is the target. And they have different roles, right? They have different slots. And mathematically, the people who do information processing, they will talk about relations as functions which take two arguments. One is the position, or the representation of the reference object, and one is of the target object. And then these reference frame issues are about, in which form are you getting that input, in which kind of coordinate frame do you get that input. Good. Yeah, and I'll come to this, rather than say it here in the abstract, I'll come to this later. So how do we do this in DFT? So in DFT, the grounding, this would be, let's say you're scene, and you're getting a phrase like the red to the left of the green. We use these very simple things with red and green and so on because we want to do this with our simple feature fields. And in the meantime, we've also done this with categories and so on, but I'm not explaining that here. So for instance, the red to the left of the green implied the red object to the left of the green. What you want as a grounding is that you have some representation that will be here a 2D field where there's an attentional peak at the location of the red, and you might have a representation also of the reference object, so maybe another near field where there's a peak at that reference location. And the way we'll do that is having some kind of we call it neural operator. There's some field or a set of connections, and you can sort of see here at a certain stage, you can kind of guess that that's the left of operator that will have positive weights here and maybe none or negative weights here. So if something falls into this, it helps form a peak. And if it falls here, it doesn't. And you can already guess that there's a reference frame, coordinate frame issue, because the center of this should be here, the green object on the right? This operator should be centered on that. And so you have to shift it to the correct reference object. And that's exactly what will happen. So I'll show you these core ideas here in our order example. This is work that was, again, initially done with this cognitive linguist, John Lipinski. And then I'll show you our current state of the art in these kind of ideas. So here in this simple case, again, we're using color as a feature value, had this kind of visual input. We had 2D space in this case. And then the notion was that you're now interpreting relational phrases about the red, green, or blue, to maybe find the object analysis to show, you can even use this for description. So there are a couple of elements here. So roughly is visual input. The visual input goes directly here into this layer. This is essentially a 3D field that has two spatial dimensions, and the third dimension is color. And we're just having 3 slices. And in this old work, it was actually just, we only had these 3 slices, and in newer work, we have actually a whole field in the third direction. And we had then a way of extracting from that a purely spatial representation for the target or the reference field, and I'll talk about that in a moment. And then we had a coordinate transform, and after the coordinate transform, we had something we call the spatial operator. Let me go through that a little one by one. So one thing is to bring objects into the attention foreground, and so we're doing that here by visual search, right? So the visual search happens here in this 3D field. So for instance, if you tell this system that you're looking for the green, just green, or have just feature, right? Then you give a boost to this slice. That will be the slice input into the 3D field. And therefore, the locations at which this object comes about, this object lies, forms a peak, and the others don't. And then you're also giving the system the information that the green thing is going to be, for instance, your target. So these boosts are the encoding of the language. So when I say green and target, I'm saying the green is on something else, so that we're specifying that the target object is the green. And here, this is through these boosts that is represented. Later you'll see we'll use nodes for that. So if we do that, if we give this field a boost, then the projection that we have here from all of these slices into these 2 fields, the target and reference field, you see that only this projection here, made as a fat arrow, will be effective, because only this field is able to make a peak due to the boost. This system gets the same input, but it can't make a peak because it doesn't get the boost, and so it's too low, right? While if you, a moment later, you give a boost to red and to reference, then now a peak will form where red input is localized. That will be here on the left. And only this field is able to build a peak. So you will be, when you do the boost, you'll direct this into this location. So there's an interesting aspect again of binding, right? You see that the 3D field space color projects equally to these 2 fields, but you can actually modulate which of these projections is effective just by controlling the dynamic regime of the target. If this is close to peak building, then this input will be relevant and effective, and if this one isn't, then that input isn't. So that's something that is done in other connections models. Often they talk about gain control, where you're turning on certain connections or off, and they think about something like shunting, where you have to multiply neural connectivity, and they argue that would be nearly possible. But that is actually not really necessary. I mean, shunting might be used somewhere. Actually, it's used for motion detection, but it is not really necessary for these general operations. So that's how you would bring in a reference and a target object into these 2 fields. And then what you need to do now is to do a coordinate transform. Why do you need to do that? I mean, you could, of course, have some neural representation where you take these inputs and you have a synaptic pattern of connection that answers left for or encodes that something is to the left of something else for every possible location. In fact, that is what some of the deep networks that do this learning do. So they have a neural connectivity pattern that they learn to the left of, by getting a lot of examples of 2 objects where one is to the left of the other. And they will, now, theoretically, they could learn that for every pair of locations on the retina. But in practice, what they actually do is coach so-called weight sharing. That is, once they have learned that for one region, they copy the connectivity across the whole array. And of course, that's extraordinarily wasteful. And these deep networks essentially always just throw mass and throw computing power and memory power onto their networks, unreasonably so. I mean, beyond what nervous systems can do. And so they don't have this problem. But in the brain, this is very, very implausible. And there's actually some hint at having these kind of coordinate transforming fields. So here we're assuming that there's only one set of connectivities, which is here at the bottom, that you would have there learn the connectivities for to the left of and to the right of. So in this image, it's not so obvious, but there would be, you could see this a little bit lighter here than the left, and that indicates that you're seeing the activation. And underlying that activation is some connectivity pattern where input to this field will, excite this field on the right when this node is present, and on the left if another node is present, and so on. And this connectivity pattern, which is really the connection between these nodes and this field, that encodes the spatial operator. And so we're assuming we just have one. Now we have one such pattern that we learn for right, left, above, and so on. And we can apply it to any location now on the retinal field, because we are coordinate transforming these two fields into a reference frame where the target field is centered on the reference field. So in other words, this here is centered on the reference field. You see that it's actually it's counterintuitive. I think one of those is actually plotted the wrong way around. This one perhaps, because the reference is on the left. No, the reference. See, if this is the reference, then the target is to the right of the reference, right? So if I represent this centered on that location, that one location will be here, then I get that. So this is the representation of the target centered in the reference field. Yeah, and that's where you can then apply the spatial operators. So the spatial operators is actually one idea of concept. We have two kinds of concepts here. One is to say, I have a red node, and the red node is really just something that boosts a certain location in a field like that. And the similar green node and blue node, that is a very simple form of concept that we had before, where a neuron stands for a certain region. And here you have a relational concept where a node like that sort of excites a certain region, with a particular pattern that encodes that relationship. And then, it just does that. There's just projection between the node and that pattern. Could be learned very easily from just a few examples. So this is what we then call concepts. I mean, a neurorepresentative concept, like discrete nodes that have their meaning through a connectivity pattern to something that's ultimately sensory motor. Here, just wired up, we just defined those connections. We didn't learn them, but we had some projects where we actually learned things like that. I mean, it's always a question of what really learning means, right? These statistical learning things are just essentially fitting, telling the system it should answer this way. The actual way of how humans learn such things is another question. For instance, you might be surprised to know that small children learn the concept color before they firmly master the concept red, green, and blue. It's kind of interesting, right? So this is a complex issue of how they actually learn things. Well, you might think, well, they first learn red, green, and blue, and then they understand these are all colors. But that's not how it works. And you must assume that they see color. Of course, they know what color is. They just don't know the specific names for the specific colors. Good. So that's sort of the crude idea. And here's some simulations. In this old work, we encoded the phrase, where is the green object relative to the red object? That would be the phrase that really asks for localization. And we encoded the phrase by giving a sequence of boosts to that system. So initially, I have these nodes, and then the boost is given here to the green node here was from the outside, we gave an input, the green node goes on, and then at that time, the green boost for this year is given, and the fact that we're talking about the target means that this is boosted, and then some, if peak forms, and then, from the outside, from a fixed schedule, we next boosted the red object and boosted the reference field. And then when we're asking for the answer, no, unfortunately, yeah, when we're answering for the answer, we're boosting this bottom system here, where the peak will form, and then from the connections are reciprocal, and so the right node here goes on because that object, sorry, over here, the peak forms, and then the corresponding node goes on. And so the phrase was represented by these different boosts and nodes, and it was presented in a particular temporal order. And that system was actually quite flexible. We could do things like, where is the green object? So not actually using the relation, and then the system would create its own relation. And that would be done by boosting everything here. And then it sort of sorts itself off. You see the superposition of all the relations, and then the one for which there's matching input actually arises. So it finds out both the reference object, which was the blue. So it can say blue, and to the right of, I think, or is it to the green is to the left of the blue. And so this is left off, I think. Left off, yeah. And now it can give an interesting answer to that. And we had one more like that. I must have switched already. So where's the round, and then where is the object above the blue? You can ask for the object and the relation, and you get it as an answer. The target, and you can even do it. Keep two of those slots open. So this early model was compared to experimental data. Frankly, these data are not so constraining, but there are people who ask, you ask people to rate, for instance, how good an example of above is this here, and you have distractors, and frankly, these are relatively trivial data that essentially just concern how the shape of these kernels, how we shape the synaptic field. So it can be, I wouldn't pay too much heed to that, but people were eager there for us to have some empirical data. There's a problem as you go to higher cognition, there isn't so much real psychophysics where you have some real constraints from measuring performance. So often our work ends up just demonstrating that we can do things that humans can do. Sometimes we can say something's harder than something else that will be show up in reaction time, but these or error rates. But these error rates are qualitative, and they are very variable across tasks and depend on a lot of things and so on. So it's hard to get hard evidence here. Good. So it's not the only way to do that, and I'll skip that. Good. So now I want to show you what we currently do, and this will be something I don't explain in that level of detail, just to give you a flavor. Now you see these very complex architectures, and the real feat is that in these CEDA sessions you can actually build an architecture like that, a simple one. Now I hope that we can still manage that, but I'm sure. I mean, if Daniel doesn't come, we can get Raul to do that in the week after. So the architecture that I'll show you now is essentially what Mathis Richter did in his doctoral thesis. Daniel did his master thesis with Mathis and is currently pushing that further, right? So it's really his direction. And it is an architecture that does both grounding and describing. So just another slide to make clear what these two things mean, right? So for instance, in these more recent models, we really have an explicit representation of what we call the conceptual structure. So this is what the language machine would perhaps generate. And for instance, you have a couple of nodes. We consider them nodes, but actually they are locations in a field, and it's you will see actually we don't really do that, but in our more current work, they're really discrete places in a field, because these fields you still use binding. So the fields have a dimension, we call that the index dimension, along which you can bind things. So they still have these properties of fields, that they are sort of spatially organized. But for now, let's just think of them as nodes, discrete neurons. So you would have a couple of nodes that this is just a representation of the activation level, and we use the color to indicate their meaning, right? These will be the red, yellow, green, blue node for target, and you have the same for reference. So another neural, that would be anatomical binding. That is, you would say red as target, this one neuron, red as reference is another neuron, right? That would be anatomical binding. That is, you have a neuron for every combination of these terms. That's not a lot here. And that has its perceptual meaning really in the sense that these neurons are wired up in a way that they activate a certain region along the hue spectrum around red, which can provide input to color space fields, which are not shown here. And similarly here for this one. And then you have a node for the spatial relation. So this above node and left off, right off, below node. So when you set these nodes to a certain activation pattern, it's actually sent in the sense of a working memory where red is sustained and above is sustained, so on. That's when you're inputting the phrase and you have the conceptual structure. In our more recent work, we allow for actual syntax trees, right? We will say that the red that is above the green is below the yellow, stuff like that, right? Where one phrase refers back to something that was in a previous phrase, and that's the syntactic dependence is expressed. And that's where the binding comes in, where you have to say the red that I just mentioned is the red that I'm now talking about. And the index dimension will actually clarify that there could be multiple reds. Could say maybe the red that is to the right of the blue that is below the red that is to the left of something else. For colors, that will be a bit confusing, but if you use real objects, you can easily use phrases like that. And then we're really addressing these issues. So we're really going into language and conceptual structure. Okay, so that's a representation of the conceptual structure. And then this would be the grounded representation, the attentional representation, right? That would be a representation where you have some spatial attentional field for targets. So for instance, if this peak is active, then that's where you're attending. You have something for reference, and you have something where you activate the relation. You see there is a certain pattern of activity here that reflects that the above node activates these neurons here, then a little light blue, right? That happened from the above node. In this case, the peak has actually formed in this field because something that matches the above node is currently active. And the inputs to those fields come from the visual array. So in this case, there would be this visual array with these different colored objects, and they make these 2D inputs here into these different fields. So for instance, the green object here is at this location. There's a red object here at that location. There's another red object up here, but it was not selected. And this is, I guess, a blue object here on the left here in this location. So when you are going in this direction, so from this description to that, then you're grounding the phrase. And the input is, of course, provided to this. And if you're going from this representation would then be coming about just from this input here, from the visual scene. And you're activating these nodes. That's what when you're describing the scene. You can see that describing is, in a way, much more ambivalent or much less well determined than grounding. When you ground, you have a phrase and you find the objects that match that phrase. And you could have a case, and I'll discuss that in a moment, where there are multiple possibilities where you have to actually go through that. We studied that because we're interested in that, but it's actually not so common because usually people don't use language in a way that makes it hard to understand, right? They don't say something highly ambiguous. Maybe sometimes they do on purpose, but or as an error, but usually it's relatively unique because that's how our communicative intent, linguists call that the Greissian principle, that you're very interested in communicating effectively. While when you're describing, you could describe all kinds of things, right? If you were to describe this room, well, what are you going to describe? So you have to have some communicative intention. You have some goal, what you're talking about. Because that really reaches into higher cognitions. It's difficult to isolate that. And so we've done things about description where we were just go on salience. So we just described the most. For instance, we did something about moving objects, and we always describe moving things because they are very salient. And it is true that we're, as humans, very much talking about agents, about events, where something changes. And that is something that actually does attract our attention, that is salient bottom up. And it's also, we're very much talking about humans. A lot of our discourse is about other humans. And other humans are also very salient to us in a way that's not purely bottom up. But of course, you have to have communicative intention. And there is a project which will be my last lecture, intentional systems, where you talk about what it means to have intentions. And ultimately that goes into describing. So we have very simple forms currently only of dealing with that. So this is the architecture. That's one version. You know, we have multiple different versions. Just give looks a little complicated, but when you work with CEDA, this is of course just conceptual. In CEDA, it would be even more complicated. I'll take a little bit through it to show you that this one architecture really doesn't contain anything totally new that you are not familiar with, except for one thing, which is the topic of next lecture, which is how to generate sequences. There's this notion of condition of satisfaction that we haven't done yet, because this will now autonomously generate these sequences, not from the outside. So I think I have individual slides. This is from that paper. So here are supposed to be the nodes. So we have so these relational nodes. We have two for each. One is sort of a working memory version, which you can set, and the other is sort of the production version. And the sequence generation I'm talking about plays with these two things, where you need to know this is what I'm currently doing, and then you know this I already did. So here you see in this little square here a illustration of the synaptic pattern. So above is the synaptic pattern, and you know the more reddish the color, the more excitatory the synapse. Left off, and this is for movement. So movement towards something, movement away from something. I'll come to that in a moment. And these synaptic patterns are applied to these fields at the bottom, which are these fields that are in a coordinate frame that is centered on the reference object. You see already here a reference object. There is I think it's the below kernel, that we call this a kernel, is active. That's why these there's a little lighter blue here in these areas, and there is also a torch here, which happened. I don't know where that happens. Maybe here. I don't remember. And this, again, reciprocal. That is, if you have a certain location active here, it could also drive these nodes, and you could then say it's below. And then I think we highlighted, I want to highlight this. So I wanted to, let's start here. This is maybe easier. So this is just the visual search machine I showed earlier, right? Here's the visual array that makes 2D input, 3D input into a color space field. Space is two-dimensional. Oops. Color space field. There are two copies of that. One is one in which there could be multiple peaks, and the other one is a single peak one where you're really making the selection. So this is a simplified form of visual search. That is by inputting a Q. So for instance, here's a peak currently. That peak comes from these nodes. It will be green. So this is why the green slice is more activated. And so only the location here where there is something green has a chance to build a peak, and ultimately it will project down onto the system a peak here at that location where the green is. This is actually a field that a system that already does binding through space. That is, there's also a velocity field. So this is different velocities of objects. And so this is very active because the green was actually moving. There's a little video input here. And there is some concept nodes for leftward movement and rightward movement and stuff like that. And so that's how these are all combined. And you're actually looking at locations where combinations of such features work. What is driving that is the representation of color and motion in concept. So you have nodes for green and red and other things, and they project onto color fields that can make peaks in these. And they're, again, there are two copies of that. One is the condition of satisfaction that I'll explain next week. And so that controls these inputs. And again, it's reciprocal. You can also say that that object at that location is read by going in the reverse direction. And then similar for movement, you can say something is moving leftward and put that into the motion field and vice versa. Yeah. And so the only thing I already showed in the first slide that there is, again, another thing we call role filler binding. That is when you talk about an object, you can talk about it as a reference object or as a target object, which it's one of these two. I think this is the target representation, and that is the reference configuration. So you have every concept node in two ways. And more recent work, we're thinking essentially the grammatical roles is anatomically bound to the concepts. Actually, in our more recent work, we abstract from that. That is, there are index dimensions that are reference or target, that grammatical roles are more abstract, and then you can sort of load a particular content into these nodes, but I'll not explain that here. And this machinery up here is this sequence generation machinery, which I'll gloss over now. Yeah, and here at the bottom is this coordinate frame business. So here you have, by having these different roles, you again give a boost. Now it's sort of automatic, comes from these nodes, boost to the reference or to the target field, and therefore how you direct the flow in, or again, it goes both direction, target and reference. And there's more stuff here because we have coordinate transforms now with respect to the reference object, as I mentioned before, but also with respect to the orientation. For instance, when you have a moving object, when you say, I'm moving to this object, then that is from the point of view of the moving object, not the toward is toward that. And so what you have to do is when this is in different directions, you have to transform the representation of the potential target object as into a frame that is oriented along the direction in which the other object moves. And so it's a rotational coordinate transform. So this is an example of this intrinsic frame, like when you say in front of the car, right? That will be in front of the car now, let's say in the direction of the train moving, or something like that. So it's another coordinate transform. So this little symbol here is a symbol for this machinery that you saw earlier to do coordinate transforms, right? So you see, it contains all the machinery that you're familiar with. When I didn't explain the nodes very much in the lectures, but there's nothing special about them. So it has this nodes, it has coordinate transforms, and it has visual search, right? These three elements, and it has sequence generation, which I'll explain only next week. And that together does everything that you wanted to do. So it does actually. I already explained that. Maybe I don't have to take you through these slides very slowly. So follow in time how it does one step, the next. First selects a potential target, and then it's the reference, and then you see the kernel, and something happens. So here's an example of that really running. So the question is, what is to the right of the green object? I guess this must be the one. And the answer will be something red, I think. And so you have a representation of the reference field where the green object, visual search for green, put a peak here. You see the other things give a little bit of an input. And if I may rewind that happens as a first thing here. And this comes from the reference field being a node for green being active. And then that's the only thing actually. And to the right of there is other representation, which should be here at the bottom. This is just if the slider goes away. So this node here is to the right node, I think. I just can't see that somehow. Can I get rid of this here? Yeah, maybe like this. And so let's do that again. So this is the node to the right, and it's on, and that puts that kernel in here, and the combination of having that reference object in that kernel will that in the target field allow something to come up. So these are three possible objects, and together with that, I think it will select one of those, which is the target response is this one here. It will be selects this one, which is this thing, and then it actually reads out that this is a red thing here. I think this is the red thing. So it answers the red thing is to the right of the green. Yeah. And something similar happens here. So it's maybe can imagine. So the thing I haven't explained is that the sequence of events where one peak comes up and so on is emergent from this dynamical architecture. So that will be the next topic of next week. And you can see that that is a very critical topic because pretty much everything cognitive, you say higher cognition, now we're talking about doing something mental that is not strictly just driven by input. Remember, all neural networks pretty much in the literature are just sitting there and waiting for input and then answer something. And that is not really what cognition is. In fact, in cognition, you can close your eyes and do cognition. So in cognition, you're very actively generating activation states, and there, in the most general form, are sequences of events. This is very discrete stuff, and this is one of the principles of the brain to make categories and to make discrete events. We can do something space-time continuous, but that's mostly in the sensory motor domain. In the mental domain, it's actually much harder to do something continuous, both in terms of the contents and in terms of temporal structure. And so next week, I'll explain how sequences emerge. And essentially, basically, it's just a lot of detection instabilities where one triggers the next. Yeah, everything else I think I understood. So we can do similar things with movement. That will be the stimulus, and then the whole machinery does movement detection. And maybe I'll not go through the slide in detail. I want to make two more points before we close. So one is this hypothesis testing. So this was for us a very cool thing to do. It's a bit of a misuse, actually. Now I know why I don't see this so well. I forgot to switch the glasses. It's a bit of a distortion because if you see the scene, you wouldn't say the red cup that is to the left of the green cup. You would actually, it's kind of an odd situation anyway, with so little context. Where clearly it's this cup, right? Because there is nothing to the left of that cup. And maybe you would have to try out. It's not totally obvious. You would have to try out. Yeah. And so we were interested in that as a matter of principle. Can you do hypothesis testing? And the idea is really also reject a hypothesis, which is something would happen in a lot of cases, and a lot of our more advanced work really requires that. In the spatial language, it's not very common that you give people puzzles like that. You would maybe say something else that makes it easier. But sometimes, for instance, you might, in a case like that, you might say, the top left. Yeah, maybe that's the easiest one. But sometimes you use multiple descriptions because one isn't enough. And if you assemble multiple descriptions, you cannot actually necessarily select the one that fulfills all relationships in parallel. You have to select one and then try the different things. And say, it's not this one. It goes somewhere else. So it's not totally unrealistic that this happens. So for us, it was a really important thing to show that we can do that, and we can. And there's the boring way to go through that, and then there's the cool way, which is the simulation, where it's for some reason screwdrivers, but the system only knows color. And so here we have the phrase, the red to the left of the green, and again, it's this one. And this is chosen that this is a little closer and thus a little larger, and it will be activated first. The blue is a distractor, makes quite an input here. So it's also important to be stable against that. So the system will actually initially select the reference object the reference object is the green, right? It starts here with the reference object. It will select this green one. You can already see here in the reference field that this peak here is winning. You see actually the target field also gets input, but it will not be enough to make a peak. Because it's a little larger, and that's the hypothesis we want to reject. And it's a moment. So it has really been selected here, and now it's looking for targets for that, and doesn't find any. In this case, we had condition of dissatisfaction field. This is what I have to explain. So we have some way of detecting that. No, it hasn't worked. We haven't been able to find something, and to break off the search. And what we do then is inhibit this, so turn this off, And there's actually inhibition of return. That is, we represent what we have previously seen. So here that we say we have tried this. And so when the inhibition hits in a moment, then yeah, we keep this, and therefore next time we're not selecting this inhibited, and the next time we're finding something, we'll find the correct green one. And then with respect to that, the target candidates are these two, and then we will find the correct one from the spatial operator and find, oh, here, this is the candidates field. That is where it's just filtered all the things that match the color cue, and this is where the selection happens. And so this is an example of hypothesis testing. Again, the cool thing is that it's autonomous, and that I haven't explained exactly how that works. Yeah, and then the last topic is to push this one step further. So one could really say this is higher cognition because it does this relational stuff and so on, but in a sense, it's still very sensory motor level, right? Because we're really driving this from the image. And so we did this project a couple of years ago, and I'm still supposed to write a journal paper about this, but we've published this as a conference paper. And that is mental mapping. So it was inspired by work that was done here in Gießen, someone called Markus Knauf, and his then postdoc Ragni, who is now a professor in Leipzig, I think, or somewhere there. Yeah, I think in Dresden, maybe Leipzig. And it does something similar like that, but purely mentally. So they do things like they get a sequence of propositions, the participants, right? And they don't do it with colors, they do it with categories like cars, like the Porsche is parked left of the Volkswagen and the Mercedes is parked in front of the Jeep, and so on. They give you a couple of things like that. And then they ask you, so where is the Porsche parked relative to the Jeep? And we do this here with colors just so because our machine uses only our neural representations, these colors. When you do this colors, it's actually kind of harder to memorize that because you're just trying to do this mentally. And people can do that, and there are some certain properties they have. The main property that we model here is that when you build up a mental map like that, there can be, for instance, you say there was, let's say, the Volkswagen, and then to the right of the Volkswagen is a Porsche, and later you hear that to the right of the Volkswagen there is an Opel. And do you put it between the Porsche and the Volkswagen, or do you put it outside? And the property is that you always put it outside. That is, you do that in a way that does not disturb the relations you already used. That's so an empirical observation. That's sort of the thing that we try to model here. You see, it's kind of hard to do psychophysics on that, right? So it's very much based on very simple things like that. And so the architecture that does that is very much like that. I mean, this is not at the time it's the same architecture. Actually, unfortunately, in the later paper, we did the graphical representation a little differently. Like now the nodes are on the left or on the right, but this is actually just a subset of the previous architecture. Now, whether it's the visual search machine, here's the coordinate transforms, here are the spatial nodes, here are the color nodes in the two roles, reference and target. That's all that it is. It's now just color, it doesn't have movement, it's simplified. The only difference is the visual search machine doesn't get actually visual input from the visual array. There's no visual array. You're not looking at the scene. There is actually a mental map. There's a purely spatial thing. And we fill that mental map by intentionally selecting things just based on the cues. When we get a blue reference cue, there will be ultimately some peak being formed, and then that blue thing generates this is again, these two are just different, that multiple peaks can be here and a single peak only here. So when you have generated a blue object, you put it at some location, and by default you put it if there's nothing else, by some small bare biasing, you put it in the center of the representation. And then where you put the next kind of thing is controlled by the relations. So if you put in a relation here, then actually I have a more detailed explanation of that. When you I didn't actually put all the detailed slides in there, but let's explain the core thing is when you are now putting a new element into this map, then the spatial operator that is active at that moment will determine where that peak exactly is, and that will be influenced by the objects in this map are little inhibitory influences here, and these inhibitory influences shift around where that new object is formed from the relation to the left of, and if there's already something left of, it's going to shift out a little further, and that is then the location at which this is entered into the map, right? Kind of cool. And so here's an example where these three were already formed, and the values red, green, and so on. They are of course not in this map. They are stored in that you have concepts, red color concepts which were set somewhere. And so you can look up what is there and just put the label here. And so it's putting in the blue here. So what it gets as an input is the phrase, where is it here? This the blue, actually, I don't even remember so quickly. Sorry, I want here, this one. And let's see here. So somewhere we're setting the relations to the right of, and we're setting the color, it should be blue to the right of red, and this is set here in these nodes. And the machinery ultimately will then put the new thing here. I'm already, for the guide, I put in that machine here. And now all these different steps in between, I don't recall. Yeah, this when the relationship comes in, and I'd have to actually myself familiarize myself with what is being shown here. But you can see ultimately just is at the right point. You can maybe get some sense how all these elements together can do that. And so if you've done it, so you could build by one phrase and other, you build a map where there are certain spatial locations assigned just on the basis of spatial relations to previous objects, and by having the color queue, you can selectively load these previous objects into the reference or target fields, depending on the phrase that you're using, and then find the object that is typical to the right of, with a subtle interaction with what is already in the map. And when you have that complete map, now you can work on that map just like on visual input. So now you can do inference consists of now answering questions about that map. Like you built the map from a few relations, and now you can ask for a new thing like, where is the blue relative to the green? And I guess there's some way how that can be answered, which I don't. The blue relative to the green should be to the right of, I guess. And so I already put here that this one's going to come on in the end, right? And again, without understanding all the details, you can imagine that the machinery can do that. And it will in the end. It does the same thing now, but retrieving locations from the spatial map, looking up what color there is, and so on. And there it answers to the right of. And so it's kind of interesting. I mean, again, this autonomy is the non-trivial thing, and I haven't explained that. Maybe another point that is useful here. This is just one big neural dynamic system, right? You're now familiar with these architectures. You've simulated them in CEDA, it's all just neural fields coupled together. So they're all just making peaks or deleting peaks or doing these various operations. So it's all space-time continuous. It's just a big dynamical system. And so when we talk about it, like I say, oh, reference color, right? This looks like information processing. Say, there is a peak here, and that means that. That is actually just us, the scientists from the outside, interpreting that. It's also how we design the model, of course. And that looks like information processing, but it isn't. It is really just neurons going on and off, right? And therefore, when I say things like it is now looking up this thing or doing, that's just way of how we talk about that, right? And that is actually really also how that happens in psychology when people talk about, this area is Broca's area, does this, and that just means when the neurons fire there, that is when from the outside it looks like we're doing this thing, but But the function is made, of course, just by the neural connectivity. And it's the fact that it's in some sense localized reflects that the brain has a specific architecture. It's not one big random system. So that certain kinds of properties, dynamic properties that then lead to those functions can be localized somewhere in the brain, right? So we can analyze our big architecture and put labels to these different subfields, because that's how these functions are brought about, by the recurrent connectivity in the system. So it's not like a deep network that's just totally intransparent and totally distributed. It's actually much more structured. It's based on localist representations, which are our core principle. And so it's maybe interesting to see that it's easy to enter just into the discourse. Even my students sometimes do that, saying, now, this does that, and that reads this, and so on. That is, but it's jargon for saying, well, this is now where the peaks form, and that's where selection, one of multiple peaks, comes up, and so on. Okay. Yeah, that's as far as I take this today.